Okay, so we've got this summary table, and I made it larger so that I can write in there so that everybody can see. And what I'm trying to convey here in this top table is going to be the relationship between the original function, the derivative, the second derivative, and the antiderivative. So let's try this. If I was told that my original function is increasing, then what I know for sure is that the first derivative is going to have to be greater than 0. But if this over here is greater than 0 and f is increasing, then what that implies is that the antiderivative is actually going to be concave up. So the sequence here is the antiderivative is concave up, which tells me that the original function is increasing, which tells me that the first derivative is positive. If all that I know is that the first derivative is positive, I can't make any claims about what's happening with the second derivative here. Okay, so that's one pattern. Another one that's going to show up is, let's say that you know that f has a relative maximum point, right? F has something that looks like that. Well, if f has a relative maximum point, then what that means is that the derivative is changing. It is changing, and so I use the triangle for change. It's changing from positive to negative, okay? Now, some people just like to say, oh, that means the derivative is equal to 0 there. It is also possible that when you have a cusp point, like that really sharp turn, that is also considered a relative max. Don't forget about that. And the derivative is not equal to 0 there. So, if we have a relative max, then the derivative changes from positive to negative. Unfortunately, that doesn't tell us anything about the second derivative. But if this is changing from positive to negative, then the antiderivative, the big guy up here, has what we call a point of inflection. It's going to change from being concave up to concave down. Unfortunately, it's a little off the screen. This is concave up. That's concave down. That's my point of inflection. Or the function is going to change from being concave down to concave up. Again, that's a point of inflection. All right, well, what are some other things that we would know for sure? If I told you that the original function was concave down, then you could tell me with certainty that f prime is decreasing. And if f prime is decreasing, then the derivative of a decreasing function is going to be negative. We also have cusp points. If you were told that f, the original function, has a cusp point, that means it has something maybe that looks like that, a really sharp point, then the derivative does not exist. And so that we can have some completion here, if you have a cusp point, the first derivative does not exist, and the second derivative does not exist. It doesn't tell you anything necessarily about the antiderivative. Other things, let's say that f has a critical point. Well, our definition of critical point, a function has a critical point if its derivative is equal to 0 or if the derivative is undefined. So that could be a relative max, it could be a relative min, it could be a saddle point, it could be a cusp point. All of those grouped together are critical points. All right, well, let's say that f double prime, let's just do another case here, f double prime changes from negative to positive. If f double prime changes from negative to positive, then the function above it is changing from decreasing to increasing. Well, what sort of a function would be changing from being decreasing to increasing? Well, that's going to be a function that has a relative minimum point. Okay, so if you're told f double prime changes from negative to positive, then what you know for sure is that f prime, the function just above that, has a relative minimum. You could also conclude that the original function, the original f of x, has a point of inflection. Okay, let's see, what else? If your antiderivative has a horizontal tangent line, or if any function has a horizontal tangent line, then when I take the derivative of something that has a horizontal tangent line, the derivative is going to be equal to 0. And I won't know anything about the first derivative or the second derivative. And we could continue playing this game forever. I'm sure we've done this plenty of times in your notes, maybe even better there. So I would refer to that. But the information in this table needs to be memorized. We need it completely. You're going to see this pattern of concave down leads to the derivative is decreasing, leads to the derivative being less than 0 a lot. So if in this last column I told you that big F, the antiderivative, was concave down, then what you could tell me with certainty is that f of x, little f, is decreasing, and that f prime is less than 0, but you wouldn't really be able to make any claims about the second derivative. Okay, so let's take that, and what I want to do is actually look at a problem. This is going to be a free response question that's going to involve a lot of writing, a lot of justifications, a lot of your defending your reaching an answer. And this is a really important skill, so if I were you, I'd make sure I have this table handy so that you can follow along as we answer the remaining questions.